We are in chapter 2. Chapter 2 is the beginning of differential calculus for us. Coming out of chapter 1, we learned about the limits. We primarily looked at the indeterminate form of the limit that was in the form 0 times infinity or 0 over 0. Now, using the idea of limits, we can now go through future chapters, since everything just about in calculus, both differential and integral calculus, is based on the idea of limits. So limits play a very central role in the whole field of calculus. Now in chapter 2, we're going to talk about the derivative of a function. In this chapter, there are actually several sections. So let's see the sections that you can see here. Let me shrink the screen a bit, and there you go. These are all the sections that are in chapter 2, a very long chapter at that. We spent about 2 weeks, if not a little more maybe, in chapter 2. So in this video, we're going to take on the topic of the derivative of the function. Now, coming out of chapter 1 again, we know about the limits of the function, and one of the things we talked about was the instantaneous rate of change of a curve. That's what we talked about. So that ties in very closely with the idea of the derivative. So the idea of derivative of a function is this. This is how it's motivated. Suppose I have a function here. So here's my coordinates, the axes. And I'm going to go ahead and draw actually a function here. This is some kind of a function, and it has to be a continuous function, by the way. So the assumption is that we are working with a continuous function. Now, in here, I'm going to draw a tangent line. Okay, so my tangent line perhaps is going to look something like this. At some point, arbitrary point A, so that's what the point A is. Okay, so the coordinates of this point therefore are A and F at A. No limits, it's just a point. Okay, and we would like to be able to actually find the slope of that tangent line. Remember in chapter 1, near the end of the chapter, we said that the slope of the tangent line is equal to the limit as A, or actually we used H, as H goes to 0 of F at A plus H minus F at A divided by H. And again, you can review the lecture that we did in section, I believe that was, it was section 1.5 maybe. But this is what we derived, the slope of a tangent line at that point. Now, if this again gave us the slope of a tangent at a point A, right? This is at x equals A. Now, what if I change the tangent line to various locations? So let's say I want to draw it here, or if I extend my curve, maybe I want to draw it here, right? The tangent line. So we would like to allow for point A to vary along the curve. Okay, and when that is the case, we just need to change or replace A with X, and that way we have the slope of a tangent at any point. So I'm going to write that the slope of tangent line at any point is going to be m of tangent is equal to the limit, as this time we're going to say H goes to 0 of, instead of A, we're going to put X, F at X plus H minus F of X divided by H. In other words, we take the limit of the difference quotient. This fraction is called the difference quotient. And that limit will give you the slope of a tangent at any point. Now, how does this have to do with the derivative? We can actually now define the derivative of a function this way. I'm going to pause the video and actually write the definition so we won't take up too much of the time. Okay, so now the process this sorry, I paused for a moment. So this definition of the derivative, I've given the definition of derivative here. So we're going to define the derivative of a function f with respect to x to be f prime x, and it's right in here, and this expression right in here. F prime x, we use the prime notation, by the way, in a representation of derivative for now. I'll show you all the notations out there and which ones we will be using. There are several. So we're using prime notation. F prime x is simply the limit of the difference quotient of f at x plus h minus f of x over h. Now, because this is a limit, remember the limits may not exist. So if the limit doesn't exist, that means the function is not differentiable at that point. Or if it exists, then we say the function is differentiable at that point. And that's what I have these bullets for you now. So remember, we say a function is differentiable, that means it has a derivative. And if a function has a derivative at a point, we also say that the function is differentiable. So that's what those two terminologies mean. Now, what is differentiation? Differentiation is simply the process of finding the derivative. That's all that is, which is f prime x for us. Okay. Now, again, I emphasize the derivative may not exist at a point, and we'll see that throughout the lecture in here. Now, let's talk briefly about the notations that we use. Notation means a way of writing something. There are actually several ways of writing this. One of them I've already used is f prime x. Okay, so that's f prime x, that's the notation. The other notation is using dx. That's how we read this one. It's dx. That's how that's read. So we're looking at ddx of f. That's another notation. The next notation here is going to be d for derivative. Subscript x means the variable, independent variable x, and the function. This means we're taking the derivative with respect to x. In fact, all of the ones I'm writing mean the same thing. Here's the other notation, d subscript x, y, instead of f of x. Some use y prime notation. dy dx, that's what Leibniz used for his notation in his calculus textbooks. We will be using that quite often. And the prime notation, I believe, was done by Newton. ddx fx is another notation. It's kind of like the second one in the list. And some engineering textbooks, they use the dot notation, f with a dot on top. And also sometimes we use, including myself, we use f prime, meaning the derivative. So if you look at this, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 different ways of showing derivatives. Okay. Now, it is possible to find higher order derivatives. So for higher derivatives, the derivative, this is the notation we use. If you use prime notation, f prime x means first derivative. F double prime x means the second derivative. F triple prime x means the third derivative. Now, we're not just going to line up these prime notations because they're not practical at some point. So we're going to use superscript 4, that means the fourth derivative, and so on and so forth. And f superscript n of x means the nth order derivative. Do we really use that many derivatives? In this course, we tend to go up to third, maybe fourth derivative, but in your second semester calculus, you will definitely go up to the nth order derivative, especially when they talk about series, Taylor series, and so forth. Using Leibniz notation, dy dx, first derivative, the superscript 2y, and then dx squared, that would be the second derivative. The superscript 3y over dy cubed, that's the third derivative, and so on and so forth, all the way up to the superscript ny over the x. Actually, this is x, sorry, I didn't mean to put y. The x, the denominators are always x, the xn. That means the nth derivative of y with respect to x. In order to get that straight, remember the numerator is the change in y, the denominator change in x. So the notation y goes on top and x in the bottom. And the derivative of the function, it is the rate of change of a function at a point. Okay, so let me write that. F prime, remember that is the slope of a tangent, and the slope means change in y over change in x. So f prime of x is the rate of change, that's what that is, of y with respect to x at any point x. Okay, that's what that is. It's a rate of change. Now, let's talk about our next idea. We did mention if the limit of the function doesn't exist, neither does the derivative, right? So let's see what's the implication? What is the implication of the limit, not the limit of the difference quotient not existing? Okay, so we're going to talk about a vertical tangent. We're talking about tangent lines here. Okay, a vertical tangent, I'll show you a graph in a moment. For us, it means the following. We're going to say that the graph of f has there you go, f has a VT, a vertical tangent line at vertical tangent line at x equals a, and this would be, as a point, it would be point A and f at a. Okay, if f is continuous at a, and if the limit of the absolute value of f prime of x is equal to infinity as x approaches a. Okay, notice we're looking at the absolute value of the function. That limit is infinity. Now, limit infinity, remember, limit of difference quotient, that's the slope of a tangent. When the slope of a tangent turns out to be infinity, which means undefined, that means the line is a vertical line. The tangent line is nearly vertical. Okay, so and this also works, by the way, for the purpose of what we do, it works with plus or minus infinity. Actually, let me write these separately, because here I looked at the absolute value of the function, so that's always infinity. Or we can also say that the limit as x goes to a of f prime of x is infinity. That means it has a vertical tangent, and the limit of f prime x equals negative infinity. It also means it has a vertical tangent. It has to do with the direction in which the line is becoming perpendicular, that the tangent line, that is. Okay, so here is, to clarify these three ideas, let's actually look at absolute value of x infinity. This would be an example of the graph of a function that has a vertical tangent. Okay, so suppose my function looks like this. Okay, and this time at 0 here, looks like I have a vertical tangent at 0. Okay, and if I draw the vertical tangent, it is going to be almost perpendicular. Okay, now again, the graph of a function, by the way, because the function is continuous, and by definition of a function, my function cannot directly drop off like that. That's not a function, right? Remember, a function at this point fails the vertical line test and it's no longer a function. But it's coming very close to being almost vertical. We're talking in a limiting sense, remember, with an epsilon of being perpendicular. That's what that is. Okay, so that is our vertical tangent for this graph. Another graph where I have vertical tangent could be, let's say, something like this. Now, if you look at the tangent line here, the slope of a tangent at point A, this one is slope is infinity. Slope of the tangent here is infinity, right? And then if you look at the tangent line being negative, and at this point, slope is negative infinity. Okay, so that's how you could have positive, negative infinities. Okay, and again, in the first case, the slope is positive, it becomes more positive, eventually it approaches positive infinity. And the other side does the opposite, it's negative, it becomes more negative, ultimately it becomes nearly perpendicular, and that gives you negative infinity. Alrighty, now we have an important theorem here. Okay, this is our theorem 1 that we're going to look at. Theorem 1 of your book goes like this: if a function f is differentiable, and remember by that means it has a derivative. If it's differentiable at point x equals a, then it is continuous at x equals a. So if the function is differentiable, then it has to be continuous at that point. Now, the other way around this does not work. Okay. Now, let me tell you a little bit about this if-then kind of statements in our theorems. So in general, the form of if-then theorems in our work is like this. Usually we say if statement P is true, then Q holds. Okay, so we say P implies Q. All right, P is called the hypothesis of the theorem. Okay, that's what P is. The T got disappeared. Okay, hypothesis of the theorem, that's what P is. Q, of course, is the conclusion of the theorem, right? So for example, if a number is even, that's P, then 2 times the number will be even. There you go. Or for example, if n is a natural number, that's the hypothesis of the theorem, then 2n would be even. That would be the conclusion. That's the Q. Okay. Now, the other type of theorems that we have, we often talk about converses of theorems. So the converse of a if-then kind of theorem goes like this: if Q, then P. That would be the converse of the above statement, the above if statement. So I have, in this case, if Q, then P. That would be the converse of if P, then Q. And then the other form of the theorem is called contrapositive. Contrapositive. Okay, so what is the contrapositive of the theorem? The contrapositive of if-then is not Q. Well, let me write the full thing for you here. If not Q, then not P. It's in the form of a negation. Okay, so those are the 3 types of statements of theorem. When we read these theorem in calculus, we got to really read them carefully, because every word, and a lot of times the words are very important. They're what they make or break the theorem. Okay, so the first theorem we have, again, it says if f is differentiable, that's the hypothesis. That means if it has a derivative, then it has to be continuous at a point. Okay, now the converse of this theorem is not true. Okay, in general, I'm just going to say converse is not true. And what do we mean by the converse, right? Well, the converse is right here. I've talked about converse here. That means if Q, then P. In our example, in this theorem, if Q means if the conclusion, then you can arrive at the hypothesis. Remember, the conclusion said that the function, it being the function, let me replace it, then f is continuous. So the converse would be if the function is continuous, then it has to be differentiable, and that is not true. Okay, so keep that in mind. If a function is continuous at a, it may not be differentiable. So here's what I'm saying. If f is continuous at a, it may or may not be differentiable at a. Actually going to work out. We're going to show that this function is continuous at 0, but it is not differentiable at 0. So first I'm going to actually, you've seen this function before. This is simply the absolute value of x. Okay, here's x and there's y. Here's 0. Now, we know the function is continuous at 0, right? Let's show that. If I take the limit as a, let's actually make this, then we're going to take the limit of f of x. So let's take a limit as x goes to 0 from the left of absolute value of x. Now, if you recall, absolute value of x can be written as a two-piece function, x or negative x, right? This is how we usually find limit involving absolute values, by rewriting them without the absolute value. So it's going to be x when x is positive, and it's going to be negative of x for negative x values. This guarantees the absolute value is always going to be positive. Okay, now, so the limit as x goes to 0 from the left of absolute value of x is simply going to be the limit as x goes to 0 from the left of negative x, and that is 0, right, by direct substitution. And then if we look at the limit as x goes to 0 from the right of x, right, that's absolute value of x equal x for x positive, and that's going to be 0 also. The right-left limits are the same, therefore the limit at that point is 0, and the function is defined. So by definition of continuity, there is an I here, right? By definition of continuity at a point, we can say that since the limit of absolute value of x equals 0 as x goes to 0 from both right and left, which is equal to f at 0, the function at 0, that means absolute value of 0, which is 0, right? Okay, so by definition of continuity, therefore, we just proved, therefore f of x is continuous at x equal 0. So this is just to show that it's continuous. Now let's show that this is not differentiable at 0, not differentiable at 0. So to do that, here's how we're going to do this. I'm just going to say differentiability of absolute value of x at x equals 0. Let's take a look at that one. So I'm going to look at the limit as h approaches 0. Okay, and we're going to come to 0, let's say, from the left. Okay, we're going to look at the slope of the tangent. Okay, we're going to look at the limit of the difference quotient now, not the limit of f of x. So as h goes to 0 from the left of negative x plus h minus negative x, right? And I just did f at x plus h, right? Divided by h. And this is going to be negative x minus h plus x. Ooh, I forgot the limits. Gotta have that. That's limit as h goes to 0 from the left. Okay. Of negative x minus h plus x over h. The x's cancel, and that's negative 1. So what we're saying is that the slope of a tangent is negative 1. And that that is confirmed. That actually is verified by the graph, right? It is confirmed by the graph. Now, let's take a look at the limit as h goes to 0 from the right. We're looking at, again, the limit at the right left of the difference quotient, and this is the difference quotient, just to show you that's the one we did up the step above. So this is going to now be the limit as h goes to 0 from the right. F at x plus h is going to be x plus h, right? Minus f of x is just x now over h, and this is 1. So if you look at this now, the slope of a tangent is negative 1 from the left, it's positive 1 from the right. Therefore, the limit actually, because that's what we interpreted, but if you think in terms of limits, you have left, right limits that are two different values. The limit as h goes to 0 of absolute value of x does not exist, because the two limits, right left limits of the difference quotient are different, therefore the limit at that point does not exist. Okay, so this is just to, because this is very important, what's with this theorem is very important. Just because the function is continuous doesn't mean it has a derivative. It's not differentiable at a point. Okay. Now, the proof of Theorem 1, actually is, it's not difficult. Let's take a look at it. So we're going to let our f of x be, actually, let me do this. I'm just going to write this f of x minus f at a, okay, is going to equal to f at x minus f at a. It's exactly what's on the left side, f at a, and I'm going to divide this expression randomly by x minus a, and we're going to multiply it by x minus a. So we haven't changed what's on the left side. Still, left and right side are equal. Now let's take the limit of both sides. Okay, so the limit of f of x minus limit of f at a as x approaches a. Okay, and this is as x approaches a also, will equal to the other side. We're going to take the limit of that fraction is the limit of f of x, the limit of f of x, okay, limit of the fraction f of x minus minus f, hold on, okay, limit of f of x minus, let me scroll this down, minus f at a divided by x minus a as x approaches a, again, everything approaches x in all of these limits. X is approaching a, okay? So times x minus a. Okay, now I'm going to keep the limit of f of x on the left side. That's the that's the limit as x approaches a of f of x equal to, I'm going to write this as limit as x approaches a of f of x minus f of a divided by x minus a times the limit of x minus a as x approaches a. And I'm going to take this negative limit of f of a to the other side becomes positive plus the limit of f at a as x approaches a. Okay, now here's, we can simplify this a little bit. Okay, so the first limit, this limit exists. That's by the hypothesis of theorem, because we assume f is differentiable. So this limit exists because we were told in the hypothesis of a theorem that the function is differentiable. The other limit, this one goes to 0 by direct substitution. When x is a, you get a minus a 0. Limit of 0 is 0, which makes the first part 0 plus, now the last part, this part, f at a is a constant. The limit of x approaching a of a constant is a constant. So that's just simply plus f at a. Okay, and we just showed that limit of f of x equal f at a, and that's the very definition of continuity. Okay, so all said and done, we just showed the limit as x goes to a of f of x equals f at a. And again, by definition of continuity, there you go, the function is continuous. So if a function is differentiable, then it's continuous. Now, if the derivative doesn't exist, usually or typically, what it means on the graph, that the graph has either a corner point, a vertical tangent, or what we call a cusp. So let me write that now. If derivative does not exist, okay, and this is at x equal a, usually that implies that on the graph we usually have either a corner point on the graph, and I'll show you what a corner point looks like in a moment. We have a corner point, or we could have a vertical tangent, or a what we call a cusp. So any one of these three things could happen, okay, at x equals a. Now for corner point, let's take a look at what happens. The corner point is this. With corner point, the right left hand derivatives, they do exist, but they are equal. So how do we classify a corner point? Again, this is when if right and comma left hand derivatives exist, but they are unequal. Okay, so in other words, f prime at a does not exist. Okay, so what does a corner point look like? There you go. That's right in here. This is a corner point of the graph. Notice the slope here, m is positive, and becoming more positive as we get near that point, and the slope of this piece is 0. So the right left points are different. Okay, so we have a corner point. Okay, now let's take a look at differentiability on an interval. Okay, so now we're going to look at, before we do, let me look at the cusp actually. So what does a cusp look like? So a cusp looks like this. This point A is a cusp. Look at the slope of a tangent. Negative, more negative, more negative, more negative, and it's becoming almost perpendicular, isn't it? And look at the slope of a line, sorry, not a line, but the slope to the curve coming from the right. The slope's positive, becoming more positive, right? More positive. These are tangent, these must be attached, right? So it's becoming more and more positive, approaching infinity, right? So here slope approaches infinity as x approaches a from the right, whereas here the slope approaches negative infinity as x approaches a from the left. Okay, and that's exactly what the definition of a cusp is. Okay, so formally we're going to define a cusp as such. Cusp, we're going to call a point A and f at A. Okay, A and f at A on the graph of f. A point is a cusp if f is continuous. F must be continuous in order to be differentiable. Keep that in mind. If f is continuous at A, and if first f prime at x, or f prime of x, approaches infinity as we approach A from one side. Okay, and it must approach f prime of x approaches negative infinity as x approaches A from another side, or the other side. Let me just put, instead of another, from the other side. And there we have it. Okay, so again, the slope here is positive and the slope here is negative. So we got the slopes coming in from different sides. Okay, now let's take a look at the right left hand derivatives. Okay, so in this case, let's say a function f is differentiable on a closed interval from A to B if f is differentiable. F is differentiable, on the open interval from A to B. This is differentiability over an interval, closed interval. So it's got to be differentiable everywhere inside of that interval. In other words, that's what we're saying here. And the limit as h approaches 0 from the right of f at A plus h minus f at A divided by h, that is the right hand derivative, and the other one would be the left hand derivative. That would be the limit as h goes to 0 from the left of f of A plus h minus f of A over h, and those two. So if this limit and the other limit exists, okay, and again the first limit as h goes to 0 from the right, that's called the right hand derivative, and the other one is the second hand derivative. This is analogous to definition of continuity over a closed interval, right? It had to be continuous over the open interval and at the endpoints. That's what this is. Okay, now let's take a look at some graphs here. For example, a vertical tangent. The graph that has vertical tangents. So for a vertical tangent, I'm going to make up a function that's like this. Again, notice here the slope of a tangent on top is positive, and the slope of a tangent as you go from left to right is positive, and it's becoming nearly at this point a vertical, almost vertical here. Okay, so the slope is undefined there. That's positive, a vertical tangent. Okay, so again, where f prime does not exist, keep that in mind. F prime, the derivative doesn't exist at corner point, at a cusp, and at vertical tangents. Okay, places where you have vertical tangent. If I have something like this, now the slope coming from left to right, as you go from left to right, for this one, is going to be, okay, so coming from the left, this is the slope of a tangent. There you go. Not sure why it's not working, my pen. The slope is less than 0 throughout the domain, right? Throughout the domain, the slope is negative for the one I've just drawn. Okay, so even in here, the slope is negative, and it's becoming nearly perpendicular. The line as we get around here, let's say, the slope is negative infinity in this case. Okay, so that would be the formation for vertical tangent. Okay, and I already showed you the corner point. For corner point, right, left hand derivatives, they exist, but they're unequal. Okay, and I stated that already. Now let's take a look at the alternative definition here. Okay, this is what we call an alternative definition of derivatives. Okay, so we have f prime of x is equal to the limit as x approaches a. Instead of h going to 0, this is also used as an alternative definition. This one uses the inspiration for this is instead of moving from a over h unit, it's moving from some point x to another point, a later point. So this is what it means. So let's say here is a, and this point is x. There you go. We're looking at the change in y over change in x. Change in y is going to be f at x minus f at a, right? And the change in x is going to be x minus a. And we take the limit of that. That means we make this point, the general point x, move in this direction, get closer and closer to point A. Okay, and that will give you the slope of a tangent at that point. Alrighty, now let's I want to show you an example. This is cool, of a function that actually, to show you that continuity doesn't imply differentiability. Okay, remember the absolute value of x, continuous, but it's not differentiable at 0. However, the other way around, if a function is differentiable everywhere, it's got to be continuous everywhere, but not the other way around. So I'm going to show you an example of that, okay, of a function that's actually continuous everywhere, but it's not differentiable anywhere, nowhere differentiable. Okay, before we actually look at some examples that we work out together here, I was going to show you an example of an interesting function. This function you're about to see is called the Weierstrass function, and it is a function that is continuous everywhere, but it is nowhere differentiable. Okay, so how can a function be like that? Remember, it is continuous everywhere. It means there are no breaks, holes, or gaps, jumps, nothing in the graph, and you cannot differentiate this function anywhere. And there it is. So this is a function that has many corners, it had many corner points, it has many, in fact infinitely many vertical tangents. And so there you go. It is, as you can see, it is a continuous function, but this function is not differentiable anywhere. So just want to again emphasize, keep this in mind. Just because you have continuity doesn't mean you have differentiability. But the other way around, if the function is differentiable, it has to be continuous. That we have. Now let's take a look at some examples actually here together. Okay, so let me show you this example. So in our example, I'm going to show you an example of a function again that is continuous at a point, but it is not differentiable. Something that we can actually see now how the detailed work turned out. So in this example, the function that I'm looking at is this function. It's f of x equals to x sine 1 over x, and then it's going to be 0 if x is indifferent from 0, and it's going to be 0 at x0. In other words, I have defined a function that is continuous at a point. Okay, and this function actually, x sine 1 over x, the limit as x goes to 0 does not exist. However, at x equals 0, because 1 over x is undefined, I have defined that to be 0, so I have a removable discontinuity at 0. Okay, so first let's take a look at the continuity. In order to show continuity, we need to show the limit as x approaches 0 of x sine 1 over x. Is it equal to f at 0? Remember, that's the condition of continuity at a point. Well, f at 0 is 0, right? That's just the way I have defined this function. Now let's find the limit of this function. And the limit, actually, if you plug in a 0 right now, you get 0 times undefined, which is an indeterminate form of the limit. The reason it's undefined infinity is because 1 over 0 is undefined, and we cannot evaluate sign of undefined. Okay. And for the purpose, by the way, of indeterminate form, whether you have 0 times infinity or 0 times negative infinity, that's still on the indeterminate. So let's show what this limit is. So I'm going to begin by bounding sine 1 over x. I'm going to bound it between negative 1 and 1. Right? Everybody agrees to that because sine has a range from negative 1 to 1. Now, if I multiply all parts of this inequality by x, this way I'm building up to the function whose limit I want to find. Okay? And this is going to be 1 times x. Now, if I look at the limit of negative x as x approaches 0, that's going to be 0. And if you look at the limit as x approaches 0 of x, the right side, this side of the inequality, that limit is also 0. So from this, we get, by, again, sandwich theorem, the limit of x sine 1 over x would be 0 as x approaches 0. Perfect. So we show that the limit of the function equals to f at 0. True. So as a result, this function, let me write, since the limit of f of x is equal to f at 0 in this case as x goes to 0, so that implies the function is continuous at x equals 0. So we're good. Now, let's see if this function is differentiable at 0. Okay, so to show differentiability at 0, let me put it as a question: is f differentiable at x equals 0? Okay, now in order to do this one, I need to do f prime. I'm going to do limit of the difference quotient. The limit as h goes to 0 of f at a is 0, a plus h minus f at a divided by h. Okay, and this is going to equal to the limit as h goes to 0 of h times sine 1 over h, right, minus f at 0 is 0. F at 0 plus h is just h, so it's just plugged in h in for x divided by h. Well, this is all gone, 0, so I can cross out the h, and this becomes simply the limit of sine 1 over h, true? The limit of sine 1 over h as h approaches 0. And that limit is undefined. It doesn't exist. This limit, dn e, does not exist. Because what's going to happen is sine 1 over h near 0, the function is going to go like that. Okay, it's just going to go crazy around 0. So again, we showed that the function is not differentiable. Therefore, f, it is not differentiable at x equal 0. Okay. Now let's take a look at other examples. Okay, let's take a look at this one example here. In this example, I want to show you that the function has a vertical tangent at a point. Okay, so in our example, let's say in this example, I'm going to let f of x be square root of x minus 2. Okay, and when that's the square root of x minus 2, the graph of the function, of course, easy to do. This is 0, here's 2, and there's a square root function that's shifted to the right 2 units. So this is what f is. Now, let's find the derivative at 2. Okay, now keep in mind the domain of this function, x must be greater than or equal to 2, right? The function does not exist for values less than 2. So let's actually do the limit as h goes to 0 of difference quotient, or difference quotient is f at a plus h minus f at a divided by h. Now, one thing, by the way, when we use the difference quotient with h will always approach 0. Okay, with x may approach a, but when you use h always approaches 0 in this definition of the difference quotient. All right, so let's actually do this. Now, h can only go to 0. Remember, h is how far away from a you are, right? So this would be 2 is where my a is. So h, for example, is a tiny distance over to the right. There is no function on the left side, right? So h cannot approach 0 from the left. There's nothing. There's no function to approach to. Okay? So h must approach 2 from the right. Right? There you go. And that is becomes 0 from the right. So I'm just going to go 0 superscript positive. Okay, now let's actually plug in h goes to 0 from the right of f at a plus h. In this case is going to be f at a is 2 plus h minus f at 2 divided by h. And this is the limit as h approaches 0 from the right of f at 2 plus h. That means you're going to plug in 2 plus h for x. That's 2 plus h minus 2 minus f at 2. That would be square root of 2 minus 2 divided by h. Now 2 minus 2 is 0. On the right, the square root is 0. So this is just the limit as h approaches 0 from the right of square root of h over h. Okay, so that's what that is. Now, to do this limit, at this point, notice we have 0 over 0, correct? Indeterminate form, so we need to work this out. Almost all of our limits end up being indeterminate forms. Okay, so h goes to 0 from the right, and I have square root of h over h. Now I'm going to multiply top bottom by square root of h, right? Remember, we assume h is not 0, so it's okay to multiply top bottom by h. And this will give me simply the limit as h goes to 0 from the right. Root h is just h divided by h root h. Give it a 1. Cross out the h's. And then when I plug in now a 0 for h, I get 1 over 0. Now 1 over 0 is not indeterminate form. That means undefined. And because the function is positive, right, 1 over h, square root of h, and this is what I mean. If you graph this, the function is positive, right? So as you approach 2, therefore, it's got to be positive infinity. So it's going to, that's what the slope of a tangent is going to be. Notice what we just found is the slope of the tangent at 2. So slope of a tangent is infinity. That means, this means we have a vertical tangent at x equals 2. So on the graph of the function, therefore, it's going to look something like this. Let me use a different color, and there you go. That is our vertical tangent at that point. So this is what we just showed, that we do have a vertical tangent at that point. Okay, let's take a look at actually an exercise in your book. This is exercise in section 2.1 of your textbook, and go up higher. This is exercise 2.1, number 8 in your textbook. Okay, in this exercise, the function f of x is 2 square root of x. Okay, and the question is asking us to use the definition of the derivative to find the derivative of the function and what is its domain. So notice, again, here is in this section, all of the exercises are found, the derivatives are found using the definition of the derivative. Later on in section 2.2 and beyond, we're going to look at actually the rules and laws of derivatives. Okay, we're going to look at some basic rules of derivatives later on. But in this section, we cannot use those methods. Again, some of you have had calculus before, and you say, oh yeah, I know how to find the derivative. The derivative, for example, I don't know, x cubed is 3x squared. You just do this and that, and that's, you don't have to do this formula. You don't have to do the limit. But in this section, this is all we know. We have no knowledge of rules of differentiation. Every single problem in this section must be done using the definition of derivatives. Okay, just want to emphasize that. So please make sure you we have to do this, because again, we don't know about those rules, and that's all this section is about. So having said that, now we want to find f prime x, right? So for all of these exercises, let me just write it. F prime of x is equal to the limit as h goes to 0, h going to 0, of the difference quotient of f at x plus h minus f at x divided by h. Okay, just in the exercise or example I did above, notice I had f at a plus h. That's because we had a single point. A was 2 right in here, right? So we want to evaluate the derivative at a point. Now we're interested in the general formula for the derivative. Now the domain of this function again has to be greater than or equal to 0. Okay, and then we'll take a look at what the derivative looks like in a moment. Now let's actually find this limit. That's going to be the limit as h goes to 0, approaches 0, of f at x plus h. So I'm going to plug in x plus h in for x minus f of x is the function, the original function, divided by h. Now we can factor the 2 out, and when we factor the 2 out, notice we have 2 square roots in the numerator. This is indeed a 0 over 0 situation. You can verify that. Okay, indeterminate. So let's work this out. I'm gonna actually go from the beginning of the line and factor the 2 out, and then this is the limit of square root of x plus h minus root x divided by h. And again, because this is in the form of a minus b, it is a binomial, and because these are square roots, we're going to multiply top and the bottom by the conjugate, which is root x plus h minus root x divided by root x plus h minus root x. And the reason, because difference of two squares will be resulted after we multiply the numerators. So that's the limit as h goes to 0 of simply root x plus h squared minus root x squared, right? Difference of two squares squared. And then denominators is h times the square root of x plus h minus root x. Okay. And then you can simplify the numerator. So this is 2 times the limit as h goes to 0 of simply x plus h minus root x divided by h times the square root of x plus h minus root x. Now, sorry, this is root. This doesn't have a square root because we're squaring the square root of x, right? So it's just going to be x. Now I can cross out in the numerator, we can cross out the x's. Once the x's are gone, h can divide out, right? Because there's a single term. Therefore, this is going to be equal to 2 times the limit of h over h times the square root of x plus h minus root x. As h approaches 0, the h is crossed out, and now we can directly substitute. Notice the 0 over 0 was just gone. That's what was giving us trouble. Now plug in 0 for h, and what are we going to get? Hold on, I multiply by conjugate. Sorry, I know most of you caught that. This should be a plus, that should be a plus. And now, but the rest is right. But I multiply by conjugate. That means the denominator, that is a plus, that is a plus. Here's my plus sign. Okay, now it looks good. Now plug in a 0 for h, and we get 2 times 1 over. So root x plus root x is what? 2 root x. And there you go, 2 root x. So the answer is going to be simply 1 over square root of x. Now again, the implied domain of this one, we cannot have division by 0 in a rational expression or in a fraction. Denominator can't be 0. But the implied domain, okay, remember, x can be greater than or equal to 0. That's for square root of x. However, 1 over root x, x cannot be 0 because division by x. Now putting these two together, therefore the domain of f prime is going to be x just bigger than 0, not including 0. Okay, now something I want to do for this one, let's actually let me just show this. Okay, so this is f of x, and we can see this kind of exercises coming up, so might as well start now. So let's say this is 2 root x. Here's x, here's y. Now at 0, of course, we showed earlier there is a vertical tangent at 0, right? For the graph of this thing, there is a vertical tangent at 0. Therefore, if I want to graph, this is the function f. I want to graph f prime that goes with this. Here is x, and this is y. There is 0. Now remember, at 0 here, if try to trace the slope of a tangent line. Okay, so let me actually do this. At 0, we have a vertical tangent, right? So vertical tangent means the slope is undefined. So this derivative function at 0 is undefined. And then the slope is becoming positive. It remains positive, but not infinity, much less. And then it's positive. But notice how it's losing steam, and the slope is actually approaching 0, right? It's the line becoming flat line, right? So this is basically how it's doing. Coming from infinity drastically drops, and then it approaches 0. This is how f prime actually behaves. Okay, we'll see more example of these in a few minutes. Some of the later exercises will ask to actually graph the function and its derivative. Remember, derivative is a function itself. So this is just a little added value to this exercise. Okay, let's take a look at another one. Let's take a look at exercise number 10. Okay, in exercise number 10, again, same section, f of x is equal to 1 over x. And we want to find the derivative again. And I emphasize we want to use the definition of a derivative, that is the limit of the difference quotient, to do this. So for this one, again, f prime of x is going to be the limit as h goes to 0 of f at x plus h. This is the general form of the derivative. So there you go. This is the derivative. You know what this is synonymous with, or not synonymous, but I should say what this resembles is like the epsilon delta definition of a limit. We learned the epsilon delta definition of a limit, the rigorous definition, and then we mentioned about the limit laws. So we didn't have to use epsilon delta to find limits. This is kind of where we are with the derivatives. This is the very foundation, very definition of derivatives. We're going to do it in this section only, but in future sections we're not going to do it this way. We're going to do it using the basic rules of differentiations. Okay, but for now it's just a passing phase. All right, let's do this one. So this is going to be f prime of x equals to the limit as h goes to 0 of 1 over x plus h minus 1 over x divided by h. Okay, now for a complex fraction is what this is. In a complex fraction, we multiply top bottom by the LCD. So I'm going to multiply the top by x plus h times 1 over x plus h minus 1 over x, and in the bottom we'll do the same thing. We're doing h times x plus h. What this will do is this will get rid of complex fraction, turns it into an ordinary fraction. Okay, so the denominator has got more factors now. But in the numerator, when you distribute the factors, the x plus h, this x plus h and that x plus h cross out. So first distribution gives you just x minus, and then let me remove that. The second distribution of x plus h times that 1 over x. Now the x's cross out, leaving me with negative of simply x plus h. True? And there you have it. And let me get that out. Okay, so the x and negative x, those cross out, and this is going to give me simply the limit as h approaches 0 of negative h over h x plus h. And then the h is cross out. Again, what we're trying to do in all of these limits is get rid of that h that's in the denominator. Okay. And now plug in for h is 0, we get 1 over x. X is x squared, and here's negative 1 over x squared. So the derivative of 1 over x is negative 1 over x squared. Later on, using the limit rules, the differentiation rules, we're going to see how to do this without finding the limit of the difference quotient. Okay, let's take a look at another exercise. Exercise number 30. We want to do the same thing in exercise number 30, in that we are given the graph of the function f, and we want to draw the graph of f prime of x. Now this is pretty cool how this works out, everyone. Now one thing to note here, by the way, before I actually graph it, let's make some observations about the function. Remember, we're interested in the slope of the tangent line. It's all about the tangent line. Slope of a tangent line, almost 0 but negative, right? So we know m is less than 0, m is almost 0. Less than 0 means the slope's negative and it's almost 0 at this point. Now notice that it's going to maintain its being negative, but it's more of a negative now, isn't it? But then in here, notice right about here, there's a transition. Slope's still negative, but it's lesser of a negative and ultimately approaches 0. At 0, slope is 0, so it's not going to be negative forever. So to me, this is what it seems like. Okay, so it's going to be almost 0, and then it's becoming more negative, right? Right about here. And then it's still negative, but it's lesser of a negative because it's ultimately got to be 0. So that means it's got to have to come back and go through here, right? So that's that portion of the derivative. Now, by symmetry, you can reflect this about the origin, what we have, and get the graph. But let's continue on. Now, coming out of to the right of 0, coming out of a slope 0, being flat, now is more positive. But look in here again. It's lesser of a positive right about here, this point. And then less positive, almost 0 again. So slope about here is going to be almost 0. Right in here is the peak, right? The peak of positivity, just as it was here. The peak of negativity was there. So that means this thing is going to have to come peak, and then it's going to go back down and go towards 0. So there you go. That's what that part of it is. And this reflects this part of the graph. So this is the graph of what's called the derivative function. This is f prime x. Although we don't even know the function f, what it is, but we can actually graph it. And the function looks like what we call a serpentine function, like a snake. This is what the serpentine function looks like. The full function is actually what you're looking at. I think that's how it's spelled. Serpentine, maybe? That's what it is. But anyhow, so that's exercise number 30 for you. Let's take a look at and see. Let's do one more, and then that's probably good enough from this section. One thing I didn't see in the exercises, let me see if I can find something with vertical tangents or corner points. Okay, this is going to be the last exercise we're going to do. I couldn't find the exercise that I liked, so I'm going to go ahead and do this one. Let's say for this function. So I'm just going to call it an example, and our function is going to be f of x is equal to the square root of 1 minus x minus 1 squared. Okay, now the graph of this function is going to be a half circle. Okay, so let me show you what this circle looks like. If I say y equals square root of 1 minus x minus 1 squared, when I square both sides, I get y squared, x minus 1 squared. And then I'm going to move x minus 1 squared to the other side. So it's y squared minus x minus 1 squared, which moves to the other side, becomes positive x minus 1 squared equals 1. Now, if you recall, this is the equation of a circle. If you look at y minus k squared plus x minus h squared equal 1, or in general it's equal to r squared. This is the equation of a circle, radius r, center at hk, right? So here h is 1 and k is 0, right? Y minus 0 squared, so that's your k. So the center is at 1, 0, radius is 1, which is the square root of the number to the right of equation which is a 1. So again, I have a circle of radius 1, center at 1, 0. And because we are looking at this portion, the full circle will look like that, right? But because we are looking at positive square root, sorry, let me draw a better circle here. This would be, let me move this one. No worries. There. This will be x. This is y. Here's 0. Remember, center is at 1, 0. And the radius is 1, so it makes it 2. So this is the graph of this function. Now, let's say we want to, again, show, or let's say we want to find, let me do that, find the slope of tangent at point 0, 0. So it looks like at 0, 0 we have a vertical tangent, right? But let's actually show that. So how do we find the slope? That would be f prime at 0, right? So that's what we want to find. So this is going to be equal to the limit as h approaches 0 from the right of f0 plus h minus f of 0 divided by h. Okay, and this is going to equal to the limit as h goes to 0 from the right of, well, f at 0 plus h is just f at h, and f at 0 in this case, you put 0 in for the function. Well, let me just carry that one more step, divide by h. Now f at 0 ends up being 0 because you put 0 in for x. That's negative 1 squared is 1, 1 minus 1 is 0. Okay, so that's equal to the limit as h approaches 0 from the right. Again, we have to approach 0 from the right because there is no graph on the left, to the left of 0. The function's domain is between 0 and 1. Let me just write that. I'm sorry, 0 and 2. Okay, anything else outside of that, the function becomes an imaginary function. It's not going to be a real function. Now, f at h is going to be simply square root of 1 minus h minus 1 squared. F at 0 we showed was 0 divided by h. And this would be limit as h goes to 0 from the right of, and let's see, let's multiply top bottom by conjugate, right? By conjugate of the numerator, which is just the square root, right? Let's just multiply by itself, right? The conjugate of numerator is just the numerator because you have 0 here. So in other words, I have 1 minus h minus 1 squared over h multiplied by another 1 minus h minus 1 squared over square root of 1 minus h minus 1 squared. That's the limit, h going to 0 of, the numerator is going to be 1 minus h minus 1 squared. Okay, and the denominator is going to be h times the radical, 1 minus h minus 1 squared. Okay, now we can take the limit. If you expand the binomial, this is what we're going to get. This is the limit as h going to 0 from the right of 1 minus h squared plus 2h minus 1 over h times the square root of 1 minus h minus 1 squared. Okay, and these cross out. And all said and done, this is going to be limit as h goes to 0 from the right of 2 minus h divided by square root of 1 minus h minus 1 squared. In the numerator, there you go, a factor of the h times, remember there's an h in the denominator, that h is here. Okay, so I can actually now cross these out. And direct substitution for h gives you 2 over 0, right? Now a number division by 0 is undefined, so this is going to be infinity. The question is it positive or negative infinity? And again, if you look at the sign chart here, the sign chart, this is 0, this is 2, and this is f of x. Between 0 and 2, the function is positive, right? You see this sits above the x-axis, so the function is positive. And because the function is positive, as you approach 0 from the right, it has to be positive infinity because the function is positive. So this shows that f has actually a vertical tangent. Therefore, f has a vertical tangent at 0, 0. Okay, and with that we are done with this lecture finally.